Okay, this is part 3 of the 4-phase power superconductivity understanding of frequency is power energy density. So we're still in the same wave pattern, but I wanted to break up the video in 3 components. We talked about power, then we talked about DC. Now we're going to talk about AC and the dynamo effect that Nikola Tesla was looking for. But unfortunately, like I said in the previous videos, he just simply did not have an oscilloscope. If he would have had an oscilloscope, I believe we would already be here today, because he could have defeated greed with the simplicity of this. Possibly. I'm not quite sure if his motive would have been as pure as mine, because he didn't understand something about electromagnetism because the grid was too young, and that understanding is how it affects the photosynthesis cycle that I've talked about. So now let's talk about AC, but we're going to stay on DC for a minute just to refresh you. Hertz, 100% duty cycle, AC DC voltage, and when you ask it at that sweet spot to give another load, the light bulb does not dim. A little bit comes right back. Okay? Versus when you go below the sweet spot, even though the volts are the same, come down here below 41.8, okay, and now you hit the light and the light clearly dims, even though the voltage drop is the same. It has to do with the hertz and frequency. Now we're going to go to AC. Remember, coming out of the power supply, there's no frequency whatsoever. AC nor DC. Now we have millivolts of AC, still turning a DC motor. Okay? Very smoothly, by the way. When it's hooked up directly to the power supply, it chatters. There's the hertz, AC. 1 hertz equals 1 volt, 1.6 joule. There's the percentage AC. Okay. Now we're going to turn up the power a little bit. In your home, it's below 50. Perfect power is 50. Okay, you see how it turns up? And now we're going to pulse the light. You see how it goes to almost 100% perfect over unity power on AC the moment you ask it to pulse. When you turn on your power at home, it goes below 50% duty cycle. That's your KVAR sending back reactive power to the grid, fighting up against their generators. In this fashion, I'd gladly take that load. No problem. When you turn on your power during a hot day, they say it's overloading the grid and our generators have to work harder. It's not because you're consuming the power. It's because you're generating reactive power up against their active power. And so it's like two generators fighting each other, or two motors fighting each other, either way you want to look at it, because they can't defeat that. So it overloads them, so they have to raise their potential to meet that demand. That's why during the hot day, when you have all the air conditioning and all that on, and then you have solar on top of that, pushing it back in the grid, their generators cannot turn down like this can. And they just overload and overheat. So they have to shut them off, which costs them money ultimately, and power plants close. You think that's a good idea, but it's technically not a good idea. Because ultimately what will happen is, if there's no power plants to balance that load, your solars will all fight against each other and make the problem worse. That's a fact. There has to be a balanced load to bounce back that energy, because energy cannot be destroyed, it just can convert forms. So this video is a little shorter because AC is a little simpler to understand, because you have bounce and bounce back, the positive and negative on and off switch, the back EMF. And so you technically, in the 4-phase superconducting power grid and power plant that we're producing, we can turn our motors down, or generators down, to a minimum of 1/4 the speed of a regular generator, and still give you all the power that you would ever need. No problem. Take it, absorb it, and send it right back to you as perfect clean power. So the same principles do apply for AC. Yeah, there's your hertz. Even though the motor's slowing down, the hertz are staying the same until we get past the sweet spot. Okay, now the motor's going very slow. I should say the dynamo is going very slow. The light is off. It's got a little bit of residual. This light's on, and this one's holding fast. Okay? Lights off, holding fast. On AC, now we're up at 50 volts, so we know that on DC, our duty cycle is 100%. And our duty cycle on AC is clearly over producing reactive power. Producing reactive power. When you do that, I'm under load with both lights, and I'm still producing reactive power. What that will do is it will make a generator in the power plant run easier, not harder. It's giving them power, something they cannot accept. Even though it's a little bit of play on words, because you're giving them reactive power, but when it gets to them, it's active power against their active power. But when you give them reactive power, or let me say it a little clearer, when you give them active power, it turns into reactive power there. What they're charging you for, and what they love to do, is they love to mess with your mind in the kVAR calculation, which is technically a phantom calculation. It's phantom. It's completely made up. Okay? Because it's based on how much draw they have on their end. It's a complete fabrication, and they charge you for that. Just look it up. It's pretty straightforward. The dictionary says it clearly about reactive power. It was something that Edison made up to charge people, and it's stuck ever since. Because, well, they figured it can't be defeated, so we can just continue on down that road. This clearly defeats that. Defeats that whole subject. That means that as I produce power from my power plant, every person will be, their motors will run efficiently, which will impose all of the grid that's using my power as my cogeneration plants. Your electricity bill will be less. The power plant's power will be better, and they'll have to pay me more, which in turn allows me to drop the price to you, which makes them bankrupt. That is satisfying a deep-seated wish, an untold, unspoken wish. And what happens if you disclose a wish? It does not come true. This answers Nikola Tesla's dying wish. Now, after part 3, I'm gladly hopeful in the affirmations of this disclosure. You're welcome.